Hello everyone, this is Group 29 presenting the Foodie Rover Critical Design Review. My name is Mauricio Ferrari. I'm a computer engineering student. Also on this team we have Chidozari Magiro, Antonia Soto, and Alexis Gieselink, all electrical engineering students. All right, so for our project's motivation, last semester when we were deciding what to do, it was right around the time that the restaurants on campus introduced the automated cashiers. And my wait time for getting lunch went from like a good 10 minutes to a painful 20. And sometimes that's just really inconvenient because I only have 25, 30 minutes of a lunch break. And now I have to wolf down my food and I don't even have time to watch my full YouTube video. And it's just really like lunch is supposed to be a time that I can take a break from the day, but it ends up becoming stressful too. So I wanted to take this project as an opportunity to set up groundwork and a foundation for a delivery system here on campus. If you look at other campuses, a few of them have introduced what they call Kiwi bots, which is essentially the same idea as Foodie Rover. It's an autonomous ground vehicle, and it drives around campus and it just delivers food. So I just wanted to prove, one, that UCF does have the capability to do that, and two, that it doesn't need to be expensive. Like one of the big goals of this project is to do the routing completely remotely and independent of Foodie Rover's own internal systems, which is why I'm using Google Maps as API. Because oftentimes what you'll see is that these autonomous vehicles get really expensive when they have to figure out the mapping themselves, when they have to map out their environment and figure out the best routing locally.
Our main goals for this project were that Foodie Rover should be able to plan its own path to the destination remotely by contacting Google Maps. It should be able to detect static objects and stop to avoid colliding with them, and the food should be safely stored with a magnetic locking system. Some of the advanced goals were the detection of dynamic objects, avoiding obstacles by rerouting around them, having a companion app that can communicate the arrival and password, and implementing a neural network to identify objects. This slide shows the engineering specifications for this project. The robot dimension should be at least 1 cubic foot to allow for enough space to hold the food being delivered. The speed should be at least 1 mile per hour. We decided not to make this too fast to allow time for processing of all of the data being taken in and exchange of that data so that we could react in time, such as when an obstacle is being encountered. The robot should be able to travel 200 meters per trip. It should be able to carry up to 3 pounds of food. The battery life should last at least 1 to 2 hours. It should be able to sense 360 degrees around it with the sensors provided. The radius of the sensing area should be at least 1 meter to allow time for the processing of that data so that the robot can stop before it hits an obstacle. The power consumption when running should be 400 watts and when resting should be about 50. The API connection delay should be no greater than 5 seconds to allow for speedy processing and reaction time. And the locking and unlocking via the keypad should be done with at least 95% accuracy.
A key component of the software is its API capabilities. This would require Foodie Rover to have a Wi-Fi chip so that it can make the API calls.
The two servers that we'll be contacting through API are Google Maps, which will be used for routing instructions based on the destination that we put in, and Polaris, which is used for real-time kinematic positioning, a process which uses feedback from base stations to make GPS coordinates much more accurate and precise. Some additional notable features of the design is that Foodie Rover runs on continuous tracks, like a tank, rather than rubber wheels. This increases the area of contact with the ground and allows for smoother travel over a variety of surfaces, making it an all-terrain vehicle. It also allows for zero-point turning, where Foodie Rover can turn left or right without moving forward or backward at the same time. Also, the interior compartment where the food is held will be insulated in order to keep the food at the right temperature during delivery, since delivery can take a long time and people want their food to still be as hot or cold as it was when they ordered it, we decided to put insulation in the interior compartment. Also, the password is software configurable to allow for resetting between each delivery to prevent theft of food materials. So each order will have a unique password so that people will not be able to remember the password and potentially steal somebody else's food when they see it being used later. This slide shows the global block diagram for the Foodie Rover hardware, including the team member who is primarily responsible for each component. We will break this down into several subsystems based on their functionality in the upcoming slides. The navigation system includes the components that allow the robot to determine its current location and decide which direction to move. The GPS module uses satellite communication to obtain latitude and longitude coordinates. The magnetometer measures Earth's magnetic field to determine its spatial orientation, which way is north, south, east, and west. This data is passed through the microcontroller to the microprocessor, which uses the current location and orientation to determine the next movement. The motor system includes the components involved in physically moving the robot. The microprocessor uses input from the navigation system and the sensor system to determine the best direction to move. It then sends the corresponding signals to each motor driver, which in turn control the movement of the 4 DC motors, turning or moving in whatever direction is appropriate. The sensor system involves the components that allow the robot to perceive its surroundings in order to detect and reroute around obstacles in its path. 8 ultrasonic sensors measure the distance to any objects in their frame and effective sensing range. These measurements are sent through the microcontroller to the microprocessor to feed into the navigation algorithms that guide control of the motor system, allowing Foodie Rover to stop and reroute as needed. The GPIO expander is included due to a shortage of I/O ports on the microcontroller. The locking system includes the components that allow for locking and unlocking of the container that holds the delivery materials. The code is configured in the microprocessor, which then passes it to the microcontroller, which will compare it to the user entry from the keypad. Upon entry of the correct code, the microcontroller will signal the lock relay to disconnect the 12-volt supply from the magnetic lock, allowing the consumer to open the lid. The power system contains the system's power supply and each of the peripheral components to which it provides the proper operating voltages. As you can see, many components require 5 volts to operate. The motor drivers connect directly to the battery, and the lock relay uses 12 volts for activating and deactivating the magnetic lock. The voltage divider connects to an analog pin on the microcontroller to monitor the battery's charge.
This slide highlights the key hardware components of the Foodie Rover. At its core, it utilizes a microprocessor and a microcontroller complemented by additional components for system integration. Motor drivers enable Foodie Rover's movement by controlling the DC motors. It features an array of ultrasonic ranging modules for detecting obstacles, while its position and direction are tracked using a magnetometer and a GPS module. For security, a magnetic lock, keypad, and relay together form a robust locking mechanism. The system is powered by a rechargeable battery, protected by fuses and supported by a dedicated charger. The accompanying image shows our prototype integrating an Arduino Uno board for peripheral management and a Raspberry Pi to operate the motor drivers. In creating Foodie Rover, we've combined the strengths of the Raspberry Pi 4 Model B and the Arduino Uno to achieve a powerful and efficient system. The Raspberry Pi serves as the brain with its strong processing capabilities, up to 8 GB of RAM, and an advanced CPU, making it ideal for running complex algorithms and handling multiple tasks simultaneously. Its versatility is further enhanced by Wi-Fi, Bluetooth, and Ethernet connectivity, along with a full Linux operating system for sophisticated software development. We chose the Pi 4 Model B for its perfect balance of power and affordability. The Arduino Uno, on the other hand, excels in real-time hardware control, offering immediate response to sensor inputs without the latency associated with Raspberry Pi's operating system. Its user-friendly development environment allows for quick programming and deployment, and its low power consumption is critical for our battery-operated bot. The Arduino's solid I/O interface ensures direct and stable connections with peripherals. Architecture of FootyRover benefits greatly from the integration of the MCP23017 GPIO expander, which enhances our Arduino Uno by adding 16 input-output ports via I2C interface. This expansion saves GPIO pins and simplifies wiring, offering a budget-friendly way to increase functionality without needing a pricier microcontroller upgrade. Additionally, the BOB12009 level shifter ensures that the 3.3-volt Raspberry Pi and the 5-volt Arduino Uno can work together safely, allowing for high-speed bidirectional UART communication. This is essential for swift and reliable data exchange, improving FootyRover's overall reliability and efficiency. These components not only improve functionality but also boost scalability and operational dependability.
This slide, we will talk about the motor drivers. For FootyRover's movement, we selected L298N dual H-bridge motor drivers to control the four 12-volt DC motors driving its chassis. This driver enables precise dual bidirectional control of two motors at once, with up to 2 amp current per channel for strong, responsive movement. Its capability with various microcontrollers include the Raspberry Pi, which makes it ideal for movement control. It's designed for ease of use, and it features operational power LEDs and an onboard voltage regulator, while protection diodes enhance component longevity. This makes the L298N a durable and flexible choice for FootyRover's mobility. For FootyRover's sensing needs, we've selected the HC-SR04 ultrasonic ranging module. Known for its reliability in automotive context and perfect for our spatial detection requirements, it offers an accurate measurement range from 2 centimeters to 4 meters, fitting our need to detect objects within 2 meters. Its digital I/O communication ensures easy integration with the Arduino for immediate environmental response. Its cost-effectiveness and simplicity of setup allows us to use 8 sensors across the bot affordably. The module's accurate in readings and narrow measuring angle of about 15 degrees provide precise object detection for collision avoidance.
All right, now we're on to the heart and soul of FootyRover, the GPS. And I know what everybody's looking at right away. It's that price. And yes, I did get it on sale. The reason the module is so expensive is because it offers real-time kinematics capability. And real-time kinematics can basically be viewed as an extra computational layer of data. So in standard GPS modules, they're taking in data from the GNSS satellites. Now with RTK modules, they also interpolate that data with RTCM correction streams from base stations. However, base stations are very expensive. If you want one for your own, it can range from a couple $100s to thousands of dollars. But Florida's Department of Transportation does have towers, mainly at the airports, that also provide RTCM correction streams. So the idea right now is to connect to those towers, see if we're within an accuracy of a couple centimeters, and if not, there are subscription services with commercialized base stations that we can also use.
For accurate navigation, FootyRover uses the 3-axis HMC 5883L compass module, a compact low-power sensor that provides precise heading information using Earth's magnetic field. It connects to the Arduino Uno via an 12C interference, offering 1 to 2 degrees of orientation accuracy. To minimize magnetic interference, we strategically place the module away from other components and use non-ferromagnetic magnetic copper pins for connections, ensuring reliable pathfinding data for the rover.
For FootyRover's security, we've integrated an AGP Tech 60 kg electric magnetic lock with a 130-pound holding force for securing the food storage compartment. This lock is controlled by the Arduino through an SRD05 VDC CLC relay, with access managed by a 4x4 keypad for secure entry. These components ensure a reliable and secure system, crucial for protecting the integrity of deliveries. The Arduino's ability to work with a relay and keypad guarantees access is restricted to authorized individuals, playing a key role in the bot's safety and operation. For Footy Rover's power, we chose the Ovonic 100C 11.1 volt 8000 milliamp per hour 3S LiPo battery for its high energy density, allowing efficient extended operation. Its light compact design improves maneuverability and reduces downtime with fast recharge times and a low self-discharge rate. This battery supports a continuous 8 amp draw per hour, matching our need of 1 hour continuous use. With recommendations from Dr. Weeks, the safety features include overcurrent protection and thermal management to prevent damage and overheating. A LiPo balance charger ensures safe charging. The battery will be stored in a metal container with a current fuse and a thermal switch.
Here we have the basic flowchart for Foodie Rover's software stack. It starts off with the customer placing an order on the mobile app, which then communicates the destination coordinates to Foodie Rover, and Foodie Rover will then check its own coordinates and make an API call to Google Maps, and from there receive the routing instructions to go from its current location to its destination. Then we go into more of the routing logic, how it detects if there's any obstacles with the ultrasonic sensor loop, and how it determines different behaviors. I would say one of the most important ones is when it does detect an obstacle, it's going to go ahead and read in its current environment through the ultrasonic sensors and determine which side, like if an obstacle is in the front, it'll determine, okay, is there more free space to my right or is there more free space to my left? And if so, I'm going to take coordinates of whichever side has more free space and send another API call to Google Maps to give me a route to get to those coordinates instead. And like that, it will be able to go around the obstacle. For the comparison of software, there are three languages that we're using across this project: Python, C++, and JavaScript. Many of these languages are being chosen because of the environments we have. Python will be used on the Raspberry Pi to interface with ROS, and it also comes with very useful libraries like OpenCV, TensorFlow. C++ is the language of choice when you're working with Arduino's IDE, and it's also a very fast language. That's why it's great for embedded. And JavaScript works very well with React Native, which is the mobile app development tool that I'm using, and it is also very useful when implementing APIs.
This slide outlines Footy Rover's PCB components developed using Altium Designer. Key elements include the ATmega 328P microcontroller and its essential hardware, the BOB 12009 level shifter for communication between the ATmega and the Raspberry Pi, the MCP 23017 GPIO expander linking the ATmega to peripherals, a relay and the related circuitry for the locking mechanism, 3 voltage regulators, two 5-volt buck converters supporting 1 amp and 3 amp of continuous current, and a 12-volt boost converter for 1 amp continuous current. Finally, we have connectors for integrating the microcontroller with the necessary signals and to power all the components in Footy Rover, excluding the motor drivers, which are directly powered by the battery. This schematic details the ATmega connections. There is a 16 MHz external crystal for the MCU to enhance precision, stability, and performance, crucial for accurate serial communication. A reset button that facilitates development and debugging by allowing quick tests of code changes or configurations, improving usability, maintainability, and reliability. A simple voltage divider implemented for battery charge monitoring through an ATmega analog pin, and dimension level shifter. Strategic placement of testbeds marked by the designator TP are included for easy testing and troubleshooting for all schematics. This slide's schematics feature the GPIO expander and the relay circuit, highlighting their connections through well-defined ports and labels. The GPIO expander is equipped with two LEDs, a green and a red one, serving purposes such as debugging, providing user feedback, and monitoring signals. For the relay circuit, an IN4007 diode and a P2N2222A transistor are utilized. The diode safeguards the circuit against voltage spikes from the relay's coil, while the transistor acts as an effective switch, controlling the circuit efficiently. Here, we present the schematics for the voltage regulators used in the design. The TPS M863252, located at the top left, supports an input range of 3 to 17 volts, offers a 1.5% reference accuracy, and achieves over 90% efficiency with a 12-volt input. It is chosen to power the Raspberry Pi board, which requires up to 3 amps of current, aligning with the regulator's 3 amp continuous support capability. Below it, the TPS 561201 is featured with an input range of 4.5 to 17 volts, a 2% reference accuracy, and more than 90% efficiency for a 5-volt output, designated to power all the other components in the board. To the right, the TPS 55165 is specified for its 2 to 36-volt input range, a fixed 12-volt output, and an 85% efficiency, and it is used for powering the 12-volt magnetic lock. All regulators offer protection related to current, voltage, and overheating. This slide displays the PCB connectors, highlighting the use of female headers for peripherals, contrasting with the male connector designated for the Raspberry Pi. This choice is driven by the intention to use a ribbon cable for Pi connections, aiming for a neater and more organized wiring. Female headers are preferred for their enhanced physical stability in connections. Additionally, screw-in terminal blocks are employed for connecting the battery and magnetic lock wires. It's noted that the PCB lacks an on-off switch. This decision is made to allow for a switch to be directly incorporated into the battery wire, facilitating optimal placement within the board structure for easy access and functionality. This slide outlines the PCB layer configuration, showcasing the top layer on the left dedicated to a 5-volt power plane and the bottom layer on the right designated for a ground plane. Together, the planes facilitate power distribution and ground return, minimizing impedance and electromagnetic interference while boosting signal quality. This arrangement simplifies routing and improves layout organization. Trace width was meticulously determined based on the anticipated current for each connection, ensuring optimal performance and reliability. Additionally, the table at the bottom of the slide presents the layer stack manager in Altium, offering detailed insight into each layer's specifics and arrangement within the PCB.
This slide shows the final completed PCB for this project with all the components soldered on. The layout is slightly different from that of the previous several slides. We did order that board and it did work, however we decided to order an updated version that condensed the layout a bit between all of the components and made the space more efficient. Here you can see a breakdown of the budget for this project, including all hardware components and any other costs that we have incurred. As of now, the total cost to build this system comes out to $585. On this slide you can see our team's work distribution. Mauricio is the primary member responsible for the communication module, with Alexis, myself, as his secondary. As our resident computer engineer, he is also the primary responsible for the software side of this project, with all of our support. Cdr is the primary member responsible for both the motor system and the magnetometer, with myself as his secondary, and he is the primary responsible for the ultrasonic sensors, with Antonia as his secondary. Antonia is primarily responsible for the microprocessor, with Mauricio's support as the secondary. She is also primarily responsible for the PCB design, with all of our support, and for the navigation module, with Mauricio as the secondary. I am primarily responsible for the locking system and the power system, with Cdr as my secondary,